Hello everyone, my name is Zhongjie. I'm a PhD student at UC Riverside. And today I'm going to present our work, SymTCP, Eluding Stateful Deep Packet Inspection with Automated Discrepancy Discovery. This is a joint work between UC Riverside and the US Army Research Lab. So what is DPI? So you might not be familiar with deep packet inspection, but you should know when you are communicating with someone on the internet, it's not only you and the other party can see the information. There are some other parties can also see the information in your private communication. For example, the government can do censorship and surveillance on network traffic, so they can know what websites or services you are accessing. And the ISPs, they can also identify the websites or services you are using. And they may do traffic differentiation to throttle some type of traffic, like P2P traffic or video streaming traffic for their own benefits. Since the ISPs know what websites you are visiting, some of them may sell the information to some third-party advertising companies to make profits. So behind the scene, the common techniques used to extract high-level information from raw network traffic is called deep packet inspection. That is DPI. It is also the common technique used by most modern network intrusion detection systems and stateful firewalls. So you may think, I'm using HTTPS, or I'm using VPN, or I'm using Tor. So my traffic is encrypted, so I'm totally safe. But things are not that easy. For HTTPS, they can also detect what website you are visiting using the SNI field in the TLS handshake. And also countries like China have been blocking VPN and Tor traffic because they can identify these protocols using deep packet inspection. So how does DPI work? This is a common threat model of on-pass DPI. So the DPI wiretaps on a router, wiretaps a router in the path between a client and a server, and it can get copies of the network packet passing by. Then it uses its own network stack to analyze the packet, to process the packets. It first reconstructs the data stream using its own TCP implementation. Then it uses some parsers to parse the data and extract application-level information. So previously, researchers have demonstrated that they are able to defeat the DPI. So the client can send some specially crafted packets, for example, a reset packet with invalid checksum, so to disrupt the TCP state machine on the DPI. Well, this packet has no set effects on the server. So the DPI, in this way, the DPI will be desynchronized from the connection, and it will no longer be able to track the connection. However, those crafted packets are very limited, and most of them no longer work. So we try to automatically find this type of packets. We found that the DPI usually have their own customized TCP implementation, which is usually simpler than the actual TCP implementation like in Linux. And the differences between the two implementations, we call them discrepancies. And in this work, we systematically study the discrepancies between two TCP implementations, and we try to automate this process. To give you an intuitive idea of implementation level discrepancy and why it is hard to find, here is an example of a very subtle discrepancy between Linux and Snort, which is an open source network intrusion detection system. From the two pieces of code, it's very hard to when TCP processes an incoming packet, it needs to check if the timestamp on the packet is in a valid range. So from these two pieces of code, it's very hard to tell by a human if these two checks are equivalent. Because it does this unsigned integer subtraction and then convert it to a signed integer. Actually, the valid ranges of the two systems are off by 2. So using this discrepancy, we can construct a packet with a specific timestamp that will be processed differently by Linux and by Snort. And this discrepancy is very hard to be found manually. Our system, SymTCP, is designed to automatically find discrepancies between two TCP implementations. We use differential testing to do that. The idea of differential testing is that we send the same input to two different systems and observe if their responses are the same. Here we send the same packet sequence to both DPI and the server to find if the DPI will behave differently from the server. However, the problem is that the DPI is a black box, so we have no idea what potential packets may cause it to behave differently. And the search space is so huge, we have to enumerate all TCP packets, and it will take us forever. Our solution is to use the server as a reference model, and we feed the server's TCP implementation to symbolic execution. Symbolic execution will automatically explore all execution paths, including those extremely hard to find corner cases. And it can generate concrete inputs for each execution path. Because the server's TCP implementation is usually more complicated than the DPI's TCP implementation, so its execution paths are likely to cover most of the execution paths of the DPI. So therefore, we have significantly reduced the number of test cases, and we can generate highly effective test cases that can cover most of the DPI's logic. Then we feed these highly effective test cases back to differential testing to find the discrepancies. So our system consists of two components. The first is the offline symbolic execution component, and the second is the online differential testing component. I will further talk about them respectively. So although we have used symbolic execution to help us shrink the search space from all possible packets to all possible execution paths, running symbolic execution on a complex stateful program like TCP implementation would cause path explosion, especially when we are sending multiple symbolic packets. The problem worsens. So to handle the path explosion problem, we made some pruning decisions with our domain knowledge to prune away those uninteresting execution paths and only keep those may potentially lead to discovering discrepancies. First, we label some drop and accept points in the program where a packet gets dropped or accepted. Accept means the program states gets changed. And we want to ensure all those drop and accept points are covered, and instead of covering all execution paths, because different execution paths reaching the same drop or accept points are very likely due to the same reason. So we can combine them. Second, because the number of combinations of TCP options are huge, so we bound them to allow each TCP option to occur only once, and we allow at most 5 TCP options in each packet, because it's very unlikely that a discrepancy requires more than 5 TCP options. Third, we early terminate execution path once it reaches some uninteresting TCP states, for example, time wait or closed states. And more details can be found in our paper. Now I'm going to talk about how to evaluate our test cases against the DPI with differential testing. So although the DPI is a black box, here we assume we can peek into its state machine. The server and the DPI both start from some initial state. Here we call it S1. And after sending one packet, both of them go to state S2. And then we send a second packet. The server rejected the packet and remains in S2. But the DPI accepted this packet and goes to another state called S3. At this point, the states have diverged between the two systems. But the DPI is a black box, so we cannot know that at this point. So what we do is we construct some follow-up packets which will cause the state transition into some final state, which will trigger an alarm on the DPI. So we send the third packet. So the server accepted this packet and go to a final state S5. But because the DPI is already in some wrong state, so it will go to another different state and will not trigger any alarm. Therefore, we can know our test cases has succeeded, triggering some discrepancy. So this is a complete test case, which has n plus r packets. The first n packets are generated from symbolic execution, and the packets before Pn are used to set up the state, and the Pn is used to trigger the discrepancy to cause DPI and the server go to different states. And the last r packets are follow-up packets to trigger feedback from the DPI, or trigger some alarm or event logging. So we always start from the TCP listen state and end by sending some data in the established state. So here is the results of symbolic execution. We use Linux kernel version 4.9.3 as a reference model. We run symbolic execution on a 72-core machine with 256 gigabyte memory, and we send 1 symbolic packet, 2 symbolic packets, and 3 symbolic packets respectively. And we also send 20, 40, and 60 bytes length TCP packets. And we found that with 3 symbolic packets and 40 bytes length, we can cover all labeled drop points. And this gives us a data set of around 56,000 test cases, and we sampled 10,000 test cases for later evaluation. We evaluated our sampled data set against 3 DPI systems. The first is Zeek, which is formerly known as Bro, and we found around 6,000 test cases can succeed, and we summarize them into 9 strategies, and 2 of them are novel strategies which haven't been reported in previous literature. We also evaluated against Snort. Because of its more rigorous TCP implementation, we only found around 600 successful test cases, and we summarized them into 11 strategies, including 3 novel strategies. The last DPI system we evaluated against is the Great Firewall of China, which is the most sophisticated censorship system in the world. And we found around 4,500 successful test cases, and we summarized them into 12 strategies, and 9 of them are novel strategies. I would encourage you to read our paper to find more interesting details. Here I will briefly talk about 2 interesting strategies we've found. And the first is related to urgent pointer. It works for Snort because the Snort has a very different implementation of the urgent pointer than Linux. Because in the RFC, there's already some ambiguity there. So different implementations, they are free to implement their own. So in this strategy, after the 3-way handshake, we send a data packet which contains the sensitive data, and we also append some junk data after the sensitive data, and we point the urgent pointer to the junk. In the Snort implementation, it will discard all the data before the urgent pointer, but in Linux, it will only consume 1 byte urgent data. So the Snort will completely ignore the sensitive data and only got the junk data, but the Linux will only discard 1 byte and still got the sensitive data. So the second strategy is what we call an underflow sequence. It means the sequence number is less than the initial sequence number of the connection. So after 3-way handshake, we send a data packet with sensitive data, and the expected sequence number here should be x plus 1. But we set it to x minus 1, which is smaller than the initial sequence number. And we also pad 2-byte data before our sensitive data. Because when Linux receives this packet, it will trim the data and discard the bytes before the expected sequence number. But this strategy, but the Zeek and the GFW, when they see this kind of packet, they will totally ignore this packet. So Okay, so as takeaways, I would summarize our key contributions as follows. We proposed a novel approach that combines wet box testing and black box testing. In wet box testing, we run symbolic execution to extract a reference model from the server's implementation. And in black box testing, we construct some follow-up packets to infer the internal states of a black box DPI. And to the best of our knowledge, we are the first to run symbolic execution on a full-fledged TCP implementation. That is the Linux TCP implementation. And we also send multiple symbolic packets instead of a single packet, so we can reach deeper states. Our approach is highly efficient and effective, and it's an automated tool to unearth discrepancies between two TCP implementations. Our tool can facilitate DPI illusion, and it can also help developers to fix the implementation bugs. To conclude my talk, I summarize our work as follows. We propose a novel approach that combines wet box testing and black box testing, and to automatically discover TCP implementation level discrepancies between two TCP implementations. And we evaluated our approach against 3 DPI systems and found 14 novel strategies. Our work significantly improved the productivity in testing and eluding DPI systems. And we open sourced our tool. That's pretty much all of it. Thank you so much for your attention.
Hi, thank you very much for a great presentation, for interesting work. I have a small question. So, in the beginning of your talk, you rightfully mentioned the issue that this deep packet inspection is also relevant to some extent also to encrypted connections. And I wonder if you have actually done results on that, on you using your approach specifically to, to detect.
Yeah, I think our approach is general enough to help both encrypted connection and unencrypted connection, because we disrupt its TCP state machine. So we may cause the DPI to completely lose track of the connection. So it can. So before we send some sensitive data, we can use this trick so it cannot detect what protocol we are using.
And a small follow-up: did you consider doing something like this for QUIC? Would it be even possible to do something like this for QUIC? Do you know if any systems are doing actually trying to do any inspection for QUIC traffic?
Sorry, I didn't get your question.
I was asking if you are aware, are there any systems that you are aware that are doing DPI for QUIC traffic, and if you could try to adopt your technique for that?
For QUIC, we haven't, unfortunately, we haven't done any experiments on QUIC protocol.
And you're not aware of systems doing even any DPI systems which are actually trying even to look at QUIC, or are you?
Sorry, that I'm not sure.
You're not sure. Okay.
Yeah, we can discuss offline.
Great.
Hi, Ram from the University of Michigan. Great talk, thank you. So I have 2 questions. What are your thoughts about expanding this to other protocols, especially not at the transport layer? And second part, I know there's been some work on using genetic algorithms for finding evasion strategies. So have you thought about what are the pros and cons of your technique compared to that?
Sorry, can you repeat your second question?
I know there's been some work on using genetic algorithms to find evasion strategies. So have you thought about what some of the pros and cons are for that and for your work compared to that?
You mean comparing with another work?
Yeah.
Okay. Yeah, sorry, I cannot forget your first question.
what are your thoughts about expanding this to other protocols?
Yeah, so to expand this to other protocols, I think we have to run symbolic execution because we are finding discrepancies between two implementations. We have to adapt symbolic execution to make it run on the protocol implementation, which we have done some pruning decisions with our domain knowledge. And I think in order to adapt to another protocol, you have to also make some pruning decisions if it's a complex stateful protocol. Otherwise, symbolic execution may have the passive explosion problem. So comparing to another automated tool, so I think there are two aims at, they feed some existing evasion strategies to them and then use genetic algorithm to evolve those strategies to find new strategies. And kind of like they are mutating existing packets. But instead, we are trying to take implementation to find all the corner cases in the implementation. So I think it's from different angle.
All right, thank you.
Thank you.
Sorry, we're running out of time. We're running out of time. Thank you very much. And let's thank Sanjay again and recall that he's in the job market.